You flip a light switch. The room brightens. You know what just happened. Light came out of the bulb, traveled through the air, and hit your eyes. Simple. Obvious. Except Richard Feynman would stop you right there. Because everything you just said, every single part of that explanation is wrong. Not approximately wrong. Not oversimplified. Actually, fundamentally, deeply wrong. Light doesn't travel through the air. Not in the way you think. Light isn't a thing moving from here to there. And when Feynman tried to explain what light actually is, what really happens when you see, he ended up describing something so strange, so far removed from our everyday intuitions that most people just couldn't accept it. But here's the thing. It's not speculation. It's not philosophy. It's tested. It's measured. It's the most precisely confirmed theory in all of science. And it says light is nothing like what you think it is. Let me start with a question. What is light? You might say it's a wave, electromagnetic radiation, oscillating electric and magnetic fields propagating through space. That's what you learned in school, and it's not wrong exactly, but it's not the whole story, not even close. Because light is also a particle, a photon, a discrete chunk of energy that can be counted, that hits detectors one at a time, that behaves like a little bullet of electromagnetic energy. So which is it? Wave or particle? And here's where most explanations go wrong. They tell you it's both. Wave-particle duality. Sometimes it acts like a wave, sometimes like a particle, depending on how you measure it. But that's not an explanation, that's just restating the mystery. Feynman hated that kind of answer. He wanted to know what's actually happening, not what it looks like, what it is. And what he discovered, what quantum electrodynamics reveals, is that light is neither a wave nor a particle. Light is something else entirely, something we don't have a good word for because nothing in our everyday experience behaves this way. The closest we can get is to say light is an excitation in a quantum field, but even that doesn't capture it. Because the way that excitation behaves, the rules it follows are so strange that you have to rebuild your entire picture of reality to make sense of it. Here's what Feynman showed. When light goes from one place to another, when a photon leaves a source and arrives at a detector, it doesn't take a single path. It doesn't go in a straight line. It doesn't go along any one route. It takes every possible path, simultaneously, all of them. The path that goes straight, the path that curves left, the path that curves right, the path that loops around, the path that goes to the moon and back before hitting your eye. Every single path. You think I'm exaggerating. I'm not. This is the path integral formulation. Feynman's great contribution to quantum mechanics. And it's not a metaphor, it's not a calculation trick. It's a description of what nature actually does. To calculate the probability of light getting from point A to point B, you add up contributions from every possible path through space and time, and they all contribute. They all matter. Now you might ask, if light takes every path, why do we see it going in straight lines? Why does a laser beam look like a beam? Why do shadows have sharp edges? And this is where the mathematics gets beautiful. Each path contributes with a different phase, a different quantum mechanical angle. And when you add them all up, most of them cancel out. They interfere destructively. The path that goes way off to the left cancels with the path that goes slightly less far to the left. The loops cancel with other loops, but near the classical path, near the straight line path that you expect, all the nearby paths have almost the same phase. They add up, they reinforce. So even though light takes every path, the only paths that matter, the only ones that survive the cancellation are the ones clustered around the classical trajectory. That's why light looks like it goes in straight lines, not because it does, but because all the other paths cancel out. Think about what this means, really think about it. When you look at a lamp across the room, photons from that lamp are not simply traveling straight to your eye. They're exploring every possible route. Most of those routes contribute almost nothing because they cancel with nearby routes. But they're all there. They're all part of the calculation. The photon, if we can even call it that, doesn't decide which path to take. It takes all of them. Feynman used to demonstrate this with mirrors. You shine light at a mirror and it reflects. Simple. You learn the law of reflection. Angle of incidence equals angle of reflection. The light bounces off like a ball bouncing off a wall. But that's not what's happening. What's actually happening is the light is hitting every point on the mirror. Every single point. And each point is contributing to the reflection. You might think the light only bounces off one spot, the spot where the angles work out right. But Feynman showed that if you block off parts of the mirror, the reflection changes. Not just in brightness. In position, the entire mirror is involved. Cover the center and the light still reflects, but differently. The reflection is coming from all the parts of the mirror simultaneously. In fact, Feynman did something even stranger. He showed that if you design a mirror with the right pattern of grooves, you can make light reflect at impossible angles. You can make it go where the law of reflection says it shouldn't go, not by breaking the law, but by understanding what's really happening. The light explores all paths from all parts of the mirror, and you can manipulate the phases so that paths you want add up and paths you don't want cancel out. This is how holograms work. This is how diffraction gratings work. This is how the entire field of optics actually functions. Not by light following rules about angles and reflections, but by light taking all possible paths and interfering with itself. Now let's talk about speed. You know light has a speed. 300 million meters per second in vacuum, the speed of light, the cosmic speed limit. Nothing goes faster. But here's a question Feynman loved to ask. What does it mean for light to have a speed? Speed is distance divided by time, but light doesn't experience time. From the perspective of a photon, if we can even talk about such a perspective, no time passes. A photon emitted from a distant star and absorbed by your eye experiences zero elapsed time. The emission and absorption are the same event from the photon's point of view. So when we say light travels at a certain speed, we're not describing the photon's experience. We're describing how space-time intervals relate for observers like us. We're describing the structure of space-time itself. The speed of light isn't a speed light goes. It's a conversion factor between space and time in the geometry of the universe. Feynman emphasized this constantly. Don't ask what the photon is doing. Ask what we measure, what we can predict. And what we measure is that when we send light from here to there, the time it takes multiplied by a certain constant gives us the distance. That constant is what we call the speed of light. But it's not about light moving. It's about the structure of space-time. Here's another thing. Light in different materials goes at different speeds. Light in glass is slower than light in air. Light in water is slower than light in vacuum. Why? The usual explanation is that light is interacting with the atoms, getting absorbed and re-emitted, and that takes time. But that's not quite right either. What's actually happening is vastly more strange. When light enters glass, it doesn't slow down. The photons still move at the speed of light. They always move at the speed of light. What happens is the light is interacting with the quantum fields of all the electrons in the material. Every electron in the glass is absorbing and emitting virtual photons. The light you see isn't the original light slowed down. It's the collective quantum behavior of trillions of electrons all interacting with the electromagnetic field. The light that comes out the other side of the glass is an emergent phenomenon. It's the combined result of all those interactions. And that combined result propagates at an effective speed slower than light in vacuum. But the actual photons, the actual quanta of the electromagnetic field, they always move at c. The speed limit never changes. What changes is how the field configurations propagate through matter. Feynman spent years working this out. Quantum electrodynamics, QED, the theory of how light and matter interact. And what he found is that everything, every interaction, every emission, every absorption comes down to a single process. An electron emits or absorbs a photon. That's it. That's the only thing that happens. Everything else, all the complexity of optics and electromagnetism and light, is combinations of that one simple process repeated over and over. A photon traveling through space. That's an electron emitting a photon and another electron far away absorbing it. Reflection. That's an electron in the mirror absorbing a photon and emitting a new one. Refraction. That's countless electrons in the material absorbing and emitting photons in a coordinated quantum dance. It's all the same process. Electron absorbs photon. Electron emits photon. Repeated. Combined. Interfering. And here's the part that should blow your mind. Those intermediate photons, the ones being emitted and absorbed in the middle of all this, they're not real. They're called virtual photons. They don't satisfy the normal relationship between energy and momentum. They can't be observed directly. They exist only as part of the calculation, as parts of paths that contribute to the final answer. You might protest. You might say if they're not real, why include them? Because they give the right answer. When you calculate using virtual photons, when you add up all the ways they can be emitted and absorbed, you get predictions that match experiments to 10 decimal places. QED is the most accurately tested theory in physics. It predicts things like the magnetic moment of the electron to absurd precision. And it does it by including all these virtual processes, all these unobservable intermediate steps. Feynman invented a whole language for this. Feynman diagrams. Little pictures showing electrons as lines, photons as wavy lines, vertices where they meet. And you calculate by drawing all possible diagrams, all possible ways the interaction can happen, and adding up their contributions. The more complex the diagram, the smaller the contribution. But they all matter. They all contribute something. What this means is that empty space isn't empty. The vacuum is seething with virtual photons popping in and out of existence, virtual electron-positron pairs appearing and annihilating, a boiling soup of quantum activity that we can't see directly, but that affects everything. The Casimir effect, vacuum polarization, Lamb shift, all of these are real, measurable phenomena caused by what's happening in supposedly empty space. Light, when it travels through vacuum, is interacting with all of this. It's not moving through nothing. It's propagating through a quantum field that's vibrating with virtual particles, and that affects how it moves, how it spreads, how it interferes with itself. Let's go back to that light switch. You flip it. What happens? Electrons in the bulb's filament start moving, accelerating, and accelerating charges radiate. They create disturbances in the electromagnetic field. Those disturbances propagate outward, not as little bullets, not as waves in a medium, as changes in the field configuration, as quantum excitations that we call photons when we measure them. Those excitations explore every possible path to every possible destination. Your eye, the wall, the ceiling, the paths interfere. Most cancel, some reinforce. The ones that reinforce create what looks like light rays spreading out from the bulb. But it's not rays. It's probability amplitudes. It's quantum mechanical interference. It's every path at once, collapsed by observation into the specific pattern you see. When a photon hits your retina, if we can even speak of a photon as a localized thing, it doesn't gently deposit energy. It's absorbed by a molecule in one of your photoreceptor cells. Instantly. Completely. The entire energy of the photon goes into exciting an electron in that molecule. That electron shifts to a higher energy state. That triggers a cascade, a signal, eventually a nerve impulse. That's how you see. But here's the strange part. Before the absorption, before the measurement, the photon wasn't on a definite path. It was in a superposition of all paths. The wave function, the mathematical object describing the photon's state, included components for every possible trajectory. Only when the absorption happened, when the interaction with matter occurred, did one particular outcome become real. This isn't philosophy. This isn't interpretation. This is what the math says. The wave function describes amplitudes for different possibilities. Those amplitudes evolve deterministically. They interfere. They combine. But when measurement happens, when an irreversible interaction occurs, you get one outcome. One path becomes actual. Not because it was the path the photon was on, but because that's how quantum mechanics works. Feynman was always careful to say he didn't understand why measurement was special, why interaction with a detector collapsed the wave function. He could calculate what would happen. He could predict probabilities, but the mechanism, the reason why one outcome occurs and not another, that remained mysterious. And it remains mysterious today. Some interpretations try to explain it. Many worlds says all outcomes happen. Copenhagen says observation collapses the wave function. Pilot wave theory says there are hidden variables. But Feynman didn't care much for interpretations. He cared about predictions. And the predictions are clear. Light behaves as a quantum field. It takes all paths. It interferes with itself. And when you measure it, you get discrete outcomes with calculable probabilities. Now, you've probably heard that observing light changes how it behaves. The double slit experiment. Send photons one at a time through two slits. Don't observe which slit they go through, and you get an interference pattern, like waves. Observe which slit, and the interference disappears, like particles. People say observation changes reality. Consciousness affects the outcome. But Feynman would tell you that's nonsense. Observation doesn't mean consciousness. Observation means interaction. When you measure which slit the photon goes through, you have to interact with it. bounce another photon off it, do something physical, and that interaction entangles the measuring device with the photon. It creates correlations. It changes the quantum state. The interference disappears not because you looked, but because you created a physical record. You entangled the photon with the environment. You made it impossible for the paths to interfere cleanly. It's not about minds, it's about thermodynamics, about entropy, about information being recorded in the universe in an irreversible way. Light passing through both slits without measurement takes both paths simultaneously. The amplitudes from both paths arrive at the screen and interfere. That's why you get bright and dark bands. The paths where the amplitudes add up constructively, the paths where they cancel. But if you measure which slit, you create an entanglement. The state of the measuring device becomes correlated with the path. And now you can't have interference between paths because the full quantum state includes the device. The paths are distinguishable. They don't interfere. This is decoherence. This is how the quantum world becomes classical, not by some magical collapse, but by entanglement with the environment, by information spreading into the universe in a way that can't be undone. Feynman understood this deeply. He saw that measurement isn't about consciousness or observers. It's about physics, about interactions, about the fact that information in quantum systems spreads and becomes inaccessible. That's what makes outcomes definite, not observation by a person, interaction with the world. So when you turn on a light, what's really happening is a quantum field is being excited. Disturbances are propagating. Those disturbances take all possible paths. They interfere. They entangle with everything they encounter. Most of the paths cancel. Some reinforce. When the reinforced paths interact with your retina, with the molecules in your eye, an irreversible process occurs. Energy is transferred. Information is recorded. And you experience seeing light. But the light itself, the photon, it was never a thing traveling from the bulb to your eye. It was a superposition of amplitudes, a mathematical object describing probabilities, a quantum field configuration that included every possible path and every possible outcome. Only the interaction made it definite. This is hard to accept. Everything in our experience tells us things are localized. Things move from here to there. They have definite positions, definite paths, but our experience is of macroscopic objects, objects made of countless particles, objects constantly interacting with the environment, objects that are always being measured, always being observed by the universe itself through constant interaction. At the quantum level, none of that is true. Particles aren't localized until measured. They don't have paths until observed. They exist as superpositions of possibilities, as amplitudes in a wave function, as excitations in quantum fields that are spread out, delocalized, exploring all of space at once. And light, the thing you think you understand because you see it every day, is the clearest example of this quantum weirdness. Because light barely interacts with itself, photons don't collide, they don't interfere with each other in the way matter does, so they stay quantum, they stay in superposition, they stay spread out, until they hit something, until they're absorbed, until the interaction happens. Feynman devoted much of his career to understanding this, to developing the mathematics, to creating the diagrams, to teaching people how to calculate what light will do without pretending to understand what light is. Because maybe what light is isn't a meaningful question. Maybe the only meaningful question is, what will light do? What can we predict? What can we measure? And what we can predict is extraordinary. We can calculate how light bends around stars, how it scatters off electrons, how it creates particle-anti-particle pairs and high-energy collisions, how it interferes with itself in every conceivable experiment. We can predict it all, to incredible precision. Using a theory that says light isn't a wave or a particle, but a quantum field that takes all paths and interferes with itself. You flip a light switch. Photons flood the room. But they're not little balls, they're not ripples in a medium, they're excitations in a field, superpositions of amplitudes, quantum objects that defy visualization. And when they hit your eye, when they're absorbed by molecules in your retina, one particular outcome occurs. One path becomes real, not because it was the path, but because that's what measurement does. Feynman would tell you not to ask why, not to demand a picture, just to calculate, to predict, to test. And when the tests confirm the predictions to 10 decimal places, to accept that this is how nature works, even if it makes no sense, even if it contradicts everything you thought you knew. Light isn't what you think. It's stranger, more beautiful, more mysterious. And understanding it, really understanding it, means letting go of the intuitions evolution gave you and accepting what the math reveals. The light is on. The room is bright. And nothing about that is simple.